At this point, all of the routers should know about one another. We can see on screen that an adjacency just formed between BB1 and BB2. Let's verify that with a show IP OSPF neighbor command. We probably should be in privilege mode when we do that. Let's do a show IP OSPF neighbor command. There we are. And we see from the perspective of router BB2 that we know about BB1 as a neighbor, and we know about R1 as a neighbor. Let's now go over to router BB1, make sure things look good from its perspective as well. Let's do a show IP OSPF neighbor command. Looks good. We know about router R1. We know about router BB2. Finally, let's go over to router R1 and let's do a show IP route to make sure that we have reachability to, for example, the loopback interfaces connected to BB1 and BB2. We do seem to know about the 3-dot network and the 4-dot network. That's good news. However, something's still not right. If you'll notice, router R1, even though it does have knowledge of the loopback interfaces on BB1 and BB2, it still does not have any knowledge of this 10.1.2.0 network or the loopback interface of router R2. These networks, remember, live over in Area 2. Why is that? You might remember one of the requirements for a multi-area OSPF network. That requirement was that every area had to touch the backbone area. It had to be adjacent to Area 0. And if you'll notice in our topology, Area 2 is not adjacent to Area 0. Rather, Area 2 has to pass through Area 1 in order to get to Area 0. What can we do about that besides redesigning the network? One option is to create a virtual link. A virtual link will virtually tie together Area 2 with the backbone area. We can say that we will pass through Area 1 to get between these two areas. Here's how we can configure that. We need to do the configuration from the perspective of router R1, then we'll go over and configure the other end of the virtual link on R2. Since we're already on R1, let's go into router configuration mode for OSPF process ID 1, and we'll say area. We'll give the area number that we need to transit to get to the other side of this virtual link. In our example, we need to transit Area 1. So we say Area 1 virtual link, and then we give the router ID of the router at the other side of this virtual link. From the perspective of R1, the router at the other side of this link is going to be router R2. It has a router ID of 2.2.2.2. We're done with our configuration on router R1. Let's move over to router R2 and let's give a complementary configuration. We go into global configuration mode and we say router OSPF 1, and then we say area 1, because that's the area that we're going to transit virtual link, and we give the router ID of, in this case, router R1. We say 1.1.1.1. Notice that we have a message that just popped up telling us that we now have an adjacency with router R1. But didn't we already have an adjacency? We did, but we were not exchanging routing information over that adjacency, were we? No, in fact, let's do this. Let's go back over to router R1 right now. And from router R1's perspective, let's do a show IP OSPF neighbor command. Notice that we have a couple of adjacencies with router R2. One over the physical fast Ethernet link, and one over this virtual link that we just created. This is going to allow router R1 and router R2 to exchange routing information with one another. Let's prove that. Let's do a show IP route. And look at this. We now have knowledge of that 10.1.2.0 network residing over in Area 2. We also have knowledge of router R2's loopback interface, which is 2.2.2.2. And something else that's interesting to note, notice that those routes that are coming from a different area other than the areas that router R1 resides in, notice that they are tagged with an IA. If we look at our context-sensitive help, we can see that IA refers to an OSPF inter-area route. This route information is coming from another area, in other words. Finally, just to make sure that we have full reachability to all of the routers in the network, let's do a ping to all of the routers' IP addresses, all of their router IDs, in other words. Let's do a ping to our own router, ping 1.1.1.1. That was successful. Let's do a ping over to router R2 at 2.2.2.2. We'll ping router BB1 with an IP address of 3.3.3.3. And finally, let's ping router BB2 at an IP address of 4.4.4.4. That is how we configure a multi-area OSPF network when we have a non-broadcast OSPF network type, and even when we have an area that's not physically adjacent to our backbone area. That is going to wrap it up for lab number 5, where we configured a multi-area OSPF network where one of the network types for OSPF was non-broadcast. We noticed that non-broadcast had the unique feature of not allowing the neighbors to automatically learn about one another. We had to overcome that behavior with the neighbor command. Something else we observed was that if an area was not physically attached to Area 0 in a multi-area OSPF network, then it would not be able to exchange routing information with any other area. A fix for that we demonstrated was the creation of a virtual link that would tie together this other OSPF area that was discontiguous from Area 0, the backbone area. And one of the things we noticed toward the end of the lab was that from router R1's perspective, a couple of the routes showed up as inter-area routes. They were being advertised from an area that R1 was not directly attached to. We're actually going to take that concept and build on it in our next lab, where we start to see how we can summarize routes coming from another area. And what if routes are coming from an external routing protocol, something other than OSPF? There's a different way that we can summarize routes into OSPF. We'll take a look at both of those scenarios coming up next in lab number